Greetings, I'm Ted Bennett, and thank you for tuning into this video where I will show you how I design air valves for wastewater force mains. Before we get started on that, I want to remind you to subscribe to my channel, The Aquifer, on YouTube. On this channel, I'm regularly posting about pump design and other things that come up in the work that I do as a civil engineer in the water industry. Trust me, it's interesting. Okay, we're talking about air valves, every agency's least favorite thing to talk about. Most agencies that own air valves tell me that the air valves either don't work, and I've even had a few agencies tell me that air valves are not needed. I do want to tell you that air valves are most certainly important, because if these agencies did not have air valves, they would be running into all kinds of pump trouble. And I do think most of these valves do actually operate better than reported. Because without air valves, you're going to run into trouble with air binding in pumps, trapped air bubbles, and air bubbles will cause a lot of extra head loss as they compress and operate like a closed valve. And you could even get into a situation where your system will siphon or even collapse your pipe. For this video, I'm working from two design guides, one from Valmatic and the other from Dezurik, or APCO. I've put the links to both of these guides in the description of this video below. I use both of these because I thought it would be fun to show the results from both. Okay, the first thing to know is what are the types of valves? Well, you have the venting valves that let large volumes of air out of the pipe at the time of like pipe or pump startup. And sometimes this air venting happens every pump cycle. Sometimes it's just at the initial startup. Then you have the vacuum valve that lets air into the pipe at the high point to permit the pipe to drain. And lastly, you have the bleeding off of small air volumes. I call this the air releasing, to remove the entrained air. And this goes on all the time. If you need a valve that does all of these functions, you'll want to specify what's called a combination valve. For more information about that, check out the information at each of these manufacturers' sites. Okay, so let's get into designing air valves. The first thing you have to decide is where to put the valves. And here's Valmatic's recommendations. They show you what type of valve to put at each location based upon the functionality. And Dezurik, not to be outdone, has a similar diagram. I encourage you to take a look at these on your own time offline to decide for your situation what type of valves that you need. Alright, so first let's talk about air venting to remove those big air bubbles at pump or pipe startup. Right away you'll see that Dezurik and Valmatic approach the design just slightly different. Dezurik's guide works from a process of calculating the flow rate and then using the chart to select the valve size. And so for the air valves, the air release valves you see here is a straight conversion from gallon per minute to CFS. The assumption in this equation is that the air is replaced with water as the pipeline fills, as venting. Air out and water in its place. Conservation of mass. Easy. For the typical situation, a pressure across the valve in the filling situation is assumed to be 2 psi. We assume 2 psi to ensure that the valve stays open for a long enough time to permit all of the air to exit. Then, using that calculated flow, we enter this chart at 2 psi, and then we calculate the flow rate and then look up what size valve is required. And as you can see, Valmatic sort of works the other way around. They provide a straight calculation to solve for the flow rate for each diameter. Now I flip the equation around and solve directly for the required diameter. I hate iterating when I know what I want. The Valmatic equation I'm showing here is populated with the typical values that I use for pressure pipe situations. And you can find these in the Valmatic design guide. And you'll want to look at that design guide to make sure these selections are appropriate for your situation. But the 7.48 is a conversion from gallons to cubic feet. The 678 is a constant. The 0.93 is a value used in venting situations. 0.6 is an orifice coefficient. The delta pressure is still 2 psi, like we talked about before, across the valve to make sure all of the air gets out of the pipe. We don't want the valve to prematurely close. 16.7 is another factor that is used in the venting situation as the initial pressure and PSI. 520 is the temperature of the fluids in Rankine, and 1 is a specific gravity. All right, I hope you're feeling good. We're already a third of the way through this. So now we'll move over to the vacuum valve sizing calculations. This is just the reverse of exhausting air. Now we want to let air in. And it's like putting your thumb over a straw. If you put your thumb over a straw, you're not letting any air in. If you remove your thumb over the top of the straw with fluid in it, you're basically letting air to vent in, and you allow the straw to drain. That's exactly what happens here with force mains. So once again, for Dezurik, we see in their calculation, they're looking at the slope of the pipe downstream of our valve to permit direct drainage out of the end of the pipe and to look at the vacuum capabilities. Here again, we're in CFS. It's a pretty straightforward calculation if you don't overcomplicate it. Just look at your force main profile and see how it's going to drain out of the end. D is your force main diameter, and S is the slope of that pipe. Now again, we're going to go to the chart and use 5 psi as the max differential here, choosing a higher value because in this situation, with a vacuum in play, we want to put some buffer between the operation of the system and a possible vacuum. We're not trying to see how close we can get to zero because with pressure pipes and their gaskets and fittings, we really don't want to run anywhere near a negative pressure situation. The pipes just are not designed for that sort of operation. Now, back to the Valmatic calculation. Again, we're direct computing for the diameter and using my shortcut method to avoid iteration. And you'll see a few values that got switched out from the venting version. See, now we're using 5 psi for the pressure differential across the valve, and we're also switching around and using 0.79 for the constant and 14.7 atmospheric pressure for the initial pressure. All right, we're near the end. Time for the air release functionality that removes any entrained air in the fluid that we're pumping. Because like I always say too much, it's hard to pump air. In fact, it's kind of impossible. I should probably do a video about air scouring sometime soon. But for this situation, both Valmatic and Dezurik do basically the same thing. A simple calc and chart tabular lookup. So here's Dezurik's approach. Basically, they're going to use this chart with the calculated venting flow rate. Pretty straightforward. And I'll show you in the examples how to do this. And here's Valmatic's approach. They just use a table instead of the chart. Pretty straightforward. So I thought it would be fun to compare the results of each design guide. I've used both of these guides over the years, but I don't think I've ever used both of them for a project. Our example situation is a medium-sized force main running at 3,500 gallons per minute with a 20-inch force main pipe. I've worked up the air release flow rate in SCFM as well as the outflow and inflow rates in CSF or CFS working from our design plan. So here we are, removing big air. This is the venting requirement, and it looks like Dezurik is going to require a 3-inch valve. For the venting capability, as we enter the chart at 5 psi, it looks like Dezurik will recommend a 2-inch valve for this situation. And as a designer, we'll choose the larger of the venting or vacuum when picking the valve because basically the venting and vacuum function through the same orifice. And there's some good videos out there about how these valves work to show you what I'm talking about. And now sticking with the Dezurik guidance, now we can look at the air release capability. This result is a bit more interesting and it requires us to think a little bit about the answer carefully. Now, our force main is running at 150 feet of head, which is approximately 65 psi. So I entered the chart at 65 psi, but realistically, some of my air release valves are higher in elevation than my pumps or pump station. So I could conceivably require a larger valve in those situations so that I can move the air out. And for all of the sites, I think it would be easier just to recommend a 1/4-inch diameter air release opening so that the builder is not fumbling around trying to figure out which valve goes where. Now, with that, I will specify combination valves where they're required, but we'll also choose maybe release only, venting only, or even vacuum only functions when that makes sense. There's no need for a vacuum capability on a long uphill run, and vice versa. There's situations where that might just be wasteful. I get the idea of maybe simplifying it, but I don't want to waste the agency's money on functionality that they don't really need. Now, let's take a look at how Valmatic would approach the very same situation. For venting, I've come up with 2.2 inches in diameter, which I've rounded up to 3 inches. And for the vacuum functionality, I come up with 2 inches. And lastly, for the air release sizing, I've come up with 5/16 inch diameter. So to compare the results, it's interesting to see that we're getting roughly the same result using both guides, and I think this is reassuring. It's also helpful information because no matter what valve I specify, I can guarantee that a contractor is going to try picking a valve that I did not look at. Who knows? They always seem to be getting a good deal somewhere. And having these calculations to go back to for the shop drawing review for that alternate valve is super helpful, as you can quickly refer back to the original plan and the performance that you had hoped to see for each function: venting, vacuum, and air release. And once you have the valve sized, you're on your way. I do encourage you to carefully look at your system because air valving can be tricky, I'm not going to lie. And it's made even more difficult by tricky situations, even more tricky piping. Review those force main profiles. I like to look at the profiles all on one sheet or in one drawing viewport. To make sure you're getting all this straight, I encourage you to review the design guides that I listed previously and listed in the video notes below. There's a ton of valuable information in these design guides that can teach you things that I've glossed over and just trying to show you how I calculate these. Additionally, you'll want your specs to reflect the capabilities discussed above. You might even consider including the inflow, outflow, and venting flow rates right in your spec along with minimum diameters of the orifice openings. And last of all, these valves can be pretty tall. Sometimes they're almost 2 feet high. So make sure your manholes are large enough and that the force main is deep enough to accommodate the air valves. And thanks for checking out this video. If you liked it, give me a thumbs up, and I'd love to connect with you on LinkedIn. With that, I'm Ted Bennett, and thank you for watching The Aquifer. I hope you learned a little bit about air valves for force main applications. Have a great day.